All right, Kerry, you're ready to go.
Okay, thank you so much. So my talk's called Structuralism as a Stance, and as the title will suggest to some of you, what I want to do in this talk is take the conversation surrounding ontic structural realism and put it into contact with what Van Fraassen has had to say about physicalism. So to foreshadow, Van Fraassen has argued that physicalism should not be interpreted as it usually is, namely as a doctrine about what is fundamental. Rather, he says it should be regarded as a stance, that is, a set of attitudes towards certain projects in metaphysics and a set of heuristics concerning how to go about those projects. What I want to argue today is that the same sorts of considerations that support viewing physicalism as a stance support viewing structuralism as a sort of stance also. Namely, I will claim as an injunction to always foreground when doing fundamental metaphysics that the language of physics is mathematics. So what I'm going to do is the following. I'm going to start off by introducing what I take to be the core doctrine associated with ontic structural realism, which is the claim that that structure, not objects, is ontologically fundamental. In the second part, I'll argue that this doctrine cannot be regarded as true, given current physics at least, right? And that's important because ontic structuralism is supposed to be motivated directly by advanced physical theory as we now find it. And in the third part, I'll use some possible responses to that argument to float the idea that ontic structuralism should be regarded as a stance, right? Namely, as I've said, as an injunction to mathematicalize metaphysics. And whether or not you agree with that, I hope it really does become clear from that argument that the value of ontic structuralism really transcends whether or not it's true. Certainly, I think for me at least, structuralism is a stance. So some qualifiers on that. First thing to say is that this argument is not going to be fully general. I'm going to be addressing only what I call priority-based, not eliminative ontic structuralism, and I'll of course say what that means. Regarding the argument in the second part that physics doesn't support structuralism as it stands, this argument is almost trivial. You can find it, it's like a two-line argument, basically, you can find in that paper, Structuralism in the Idiom of Determination. I'll say a little bit about why this, in hindsight, obvious argument was missed. And the third thing I want to say is I'm going to be kind of going over a lot of old ground. The new stuff only comes right at the end. But to get to that point, everything's going to hang on how things are defined. So I need to go through a little bit of somewhat tedious definitions of structure and objects and things like that. So I just ask you to please bear with me. Okay, so there's lots of different ways of expressing ontic structural realism. I'm going to take my characterization from how it appears on the very first page of this wonderful book by Stephen French, The Structure of the World. So the way that he characterizes or sums up ontic structuralism is as the claim that the fundamental ontology of the world is one of structures and that objects, as commonly conceived, are at best derivative, at worst eliminable. So that claim there, I'm going to take to be the core doctrine of ontic structural realism. So the very wording there suggests that there's at least a couple of forms of ontic structural realism. The first I'll call priority-based ontic structuralism, and this, I'll just call it structuralism. Priority-based structuralism, which corresponds to the at best derivative rendering. So according to priority-based structuralism, in the domain of fundamental physics, you get objects and you get structures, but the structures are more fundamental than the objects, right? I like using the analogy of fine structure. Physics gives us a fundamental theory, structuralists take that and they fraction it into what's more and less fundamental to it. On the other hand, the at worst eliminable rendering invites a eliminative form of structuralism, according to which in the domain of fundamental physics, you'd have thought maybe there was objects as well as structure, but really there's only structure. So if you want to assess either of these positions, right, you have to say what it is you mean by these terms, right? What do you mean by structure? What do you mean by object? What do you mean by more fundamental than or ontologically prior to? Now, this latter, the notion of ontological priority is something that there's been a huge amount of work in metaphysics in recent years. I'm not going to talk much about that. I'm just going to give a very quick rendering of what I mean by that. I'm going to focus much more today on the definitions of the categories, because it's really here that structuralists have come in for a bit of flack. A lot of people have said that structuralists have yet to precisely articulate what's an object as opposed to a structure. Others have said that in principle it can't be done. There's no clear demarcation between these two things, at least not in a realistically significant way. So as Van Frassen puts it, what exactly is the difference between matter and form, content and structure? Jacob, do you want me to go on? So,
sorry for the technical glitch.
No worries there. So many people have claimed that the distinction between structure and object can't be nicely articulated, at least not in a realistically significant way. So as Van Frassen puts it, what exactly is the difference between matter and form, content and structure? Aren't such distinctions painfully context dependent? Right, so here is a kid's toy. It's an object. It also seems like there's a sense in which you could regard it as a structure, right? So how do we determine the difference between these two things? So let's take our cue. Let's start with defining how structuralists think about objects, and take our cue from that quote from Stephen before when he talks about objects as commonly conceived, right? The notion that of objects that structuralists are interested in, they claim, is gleaned from our interaction with the kind of mundane macroscopic exterior of the world, that's kind of reified into a set of metaphysical categories by traditional metaphysicians, right? So they want to think about objects as those metaphysicians conceive of them. So we associate all sorts of features with ordinary objects, right? That they're localizable, right? That they're countable, that they persist sort of long enough for me to continue to talk about them. As many of you will know, all of those are features that could be problematized in physics. Nevertheless, structuralists tend to focus on one particular aspect of our common conception of objects, and that is their supposed ontological independence, right? According to structuralists, metaphysicians conceive, as do ordinary people, as objects as kind of ontologically sovereign. They don't depend on anything else for their existence. So here's James and Don Ross. We should not interpret science, either fundamental physics or the special sciences, as metaphysically consistent to the existence of self-subsistent individuals, right? Ontologically independent individuals, or substances, if you like. So to think about what we mean by objects in structuralism, we should really think about what would make an entity self-subsistent, a self-subsistent individual. Now, it seems to me that an entity of a given kind can qualify as self-subsistent only if all of the properties that define it as an entity of that kind are intrinsic properties. Why is that? Well, just think for a moment, recall what roughly we mean by an intrinsic property. Roughly speaking, an intrinsic property is one that an entity can possess independently of what the rest of the world is like. So these are contrasted with extrinsic properties, paradigms of which are properties like being alone, right, or being a sister. So these are properties that I have right now, but I clearly don't possess these independently of what the rest of the world is like, right? So somebody walks into this room, for example, I don't have the property of being alone anymore. Somebody extinguishes an individual that happens to live in Belgium, I don't have the property of being a sister anymore. So these sorts of properties are contrasted with intrinsic properties, right? And paradigms of these for philosophers tend to be things like geometric properties, such as being rectangular, or basic physical properties like having mass 5 grams, right? Let's say this postcard has these properties. It seems that this postcard has these properties just as a matter of its own business, right? Certainly if I want to change the fact it's rectangular or that it has 5 grams, I have to kind of get up in the face of this object itself. It's not enough to do something over there where the front door is. Now, if it actually occurs to you there's nothing obvious that these are intrinsic properties, like what if there was like a thermal anisotropy in this room, such that it was much warmer over here than there, would it still be rectangular, right? What would mass say about mass being intrinsic, right? You're thinking like a structuralist, and you're not supposed to be doing that just now. You're supposed to be thinking about how traditional metaphysicians think of objects and properties. And I think it's right to say that all these properties are traditionally regarded as intrinsic. In any case, given those definitions, it seems again that entities of a given kind can qualify as self-subsistent, not depending on the existence or non-existence of anything else in order to be the way that they are, only if all properties definitive of that kind are intrinsic and hence independent of the rest of the way that the world is. So, now, I should say it's not clear to me that you find exactly that definition given of objects. That's what characterizes an object in the structuralist literature. I did find, you can find statements like this. So this is from James's book. To recap, standard metaphysics assumes that there's individuals in space-time whose existence is independent of each other. Point 2, each has some properties that are intrinsic to it. And they go on to say that they argue against all of these things. That, having some properties that are intrinsic to you is a weaker characterization that I've given, but I think here we can take that weaker characterization and say that an entity of a given kind is going to qualify as an object only if at least some of the properties that define it as a member of that kind are intrinsic properties. That's actually, nothing's going to hang on this weaker characterization. It just makes things easier for me to present. I can explain this later on. Okay, so we've got a bit of a definition of object now. So Stephen says the fundamental ontology of the world is one of structures and objects. It's commonly conceived of at best derivative, at worst eliminable. Now, nobody thinks that toys or postcards are fundamental. People think that things like electrons are. And so ontic structuralists urge the reconceptualization of electrons, elementary particles, and so forth in structural instead of individualistic terms. Okay, that's what they're trying to do. So given the two ways of thinking about structuralism, it seems these two ways to affect this reconceptualization. According to the priority-based account, they're going to say, or it's going to say that some of the properties that define electrons are intrinsic properties, right? Hence, there are things in the fundamental domain that count as objects, but nevertheless, these are all secondary to structures, right? That's how I would interpret priority-based structuralism, right, in the fundamental domain. So thus is assuming at least some of the property of having mass, the mass determinate mass that an electron has, 0.511 whatever's, spin half, charge E are intrinsic. Those properties are secondary to structure, right? That to me is what the priority-based structuralist says. What the eliminative structuralist is going to say is that none of these properties definitive of electrons is an intrinsic property. So what I want to do today is focus on priority-based structuralism, take that as my target. This is the least radical of the two, and hence you might think the easier for the structuralists to defend. Now, the reason this is less radical is because the kind properties of electrons, right, those properties that define it as a member of a given kind, its kind, are generally all thought of as intrinsic. So Alexander Bird, in his wonderful book, Nature's Metaphysics, is happy to simply say without argument, no one has suggested that charge, rest mass, and spin are not intrinsic, right? Now, that isn't actually true. I'll give some references to this at the end. But that somebody as immersed in current metaphysics of science can just say that without argument shows how orthodox an assumption it is. Okay, and as I say, I'll give some references to work questioning that these properties are intrinsic later on, but that's what we're going to assume going forward. Okay, so we have a characterization of objects already. What do we mean by priority? Well, I'm going to work with a very intuitive characterization according to which some entity X is more fundamental than some entity of Y. If and only if the facts or features of X determine all the facts or features of Y. Okay, that's pretty rough and ready. It's perfectly sufficient for our purposes. So this characterization is going to make the fundamental or the more fundamental a sufficient condition of the less fundamental. Settle the facts about the more fundamental stuff, the fact that it exists, the way that it is, and you settle all the facts about the less fundamental, right? That it exists, and that it's the way that it is. And so this sufficiency-based way of thinking about priority is motivated by common platitudes of how we think about fundamentality. So we often, or metaphysicians at least, often characterize the fundamental as all God had to do, make the fundamental stuff, everything else falls into place. That presents the fundamental as a sufficient condition on everything else. So to be clear, I'm not characterizing fundamentality in terms of ontological dependence, namely such that some entity X is less fundamental than some entity Y. If that Y ontologically depends on X, right, if it can't exist without it, that would make the fundamental a necessary condition on the non-fundamental, right? And necessary conditions and sufficient conditions are not the same thing. Okay, I'll come back to this later on, but we're thinking of fundamentality in sufficiency terms. All right, moving on. What do we mean by structure? Well, it seems to me that there's nowhere in the structuralist literature where you're going to find structuralists coming out with a set of necessary and sufficient conditions for what counts as a structure. What you find are gestural characterizations supplemented with a bunch of concrete examples of what counts as structure, together with an explicit disavowal that anything more precise than that is either necessary or desirable. So here, for example, is Stephen and James, in I think their last co-written paper together. They say, because of the width of its embrace and its complex history, defining what is meant by structure and characterizing the tendency in general is problematic. However, we begin by pointing out that the structuralist tendency always involves a shift in focus away from objects, however metaphysically conceived, to the structures in which they're supposedly embedded. This is vague, but the tendency, both historically and in its current incarnation, is not monolithic, but rather includes various overlapping subgroups of structuralists. Okay, so the basic idea here as I read it is analytic philosophers love analyses, namely sets of necessary and sufficient conditions. They make things really precise, but sometimes that precision comes at the price of losing interesting complexity, right? Losing facts about how the notion has been used historically, losing sight of the fact that it's kind of open-ended, that science, for example, is going to progress, that there might even be a kind of ambivalence about it that's constitutive of it, as people have said, for against attempts to give, analyses of love or gender or biological species, something like that, right? There's some kind of rejection that it's appropriate to just nail this one thing down once and for all. And I was reminded of this nice quote by rereading Brian Roberts' paper, very nice paper, Group Structural Realism. Now, as Brian says there, that's all well and good, but of course they've got to say something to get this metaphysics off the ground. So how should we characterize structure? Well, one thing that's seems clear, is that intrinsic properties are not going to count as structural features, right? Eliminative structuralism is all about eliminating entities that have any intrinsic properties at all. So this idea goes right back to the beginnings of structural realism, the paper that in fact coins the term by Grover Maxwell in 1970. He writes there, structural characteristics may be taken to be just those that are not intrinsic. So the trained ear in metaphysics is going to hear that as saying extrinsic properties, right? The kind of logical complement of intrinsic properties, their structural features, as well as relations between objects, right? Things like metric relations, entanglement relations that do so much work in structuralism. So those are structural features. Now, you might worry, this isn't a strict dichotomy here, because it seems there are properties that are at once relational and also intrinsic, right? Such as having a very symmetrical face, right? The property that very beautiful people are said to enjoy. That's a relational property. It tells you about how two sides of their face relate to one another, but it's just a feature about them. If you want to change it, again, you have to get right up in their face. It's not enough to sort of mess around over here and here. Now, it seems to me, and I'm not sure this is made explicit, but it's very clearly intended, properties such as that are kosher for structuralists, because while they may be intrinsic, they're fundamentally relational, right? They're defined in relational terms. So those all count as structures for structuralists. What's also clear is that laws count as structural, right? Just think back to what James was saying before. And moreover, certain mathematical structures that are not obviously construable as relations between objects or properties, right? These are going to count as structures. And absolutely most saliently for structuralists right now, group structures, right, which are the mathematical structures we use to express facts about symmetry, okay? Symmetry and invariance. So again, just think of what James was just saying. So again, here we can say that the fact that, say, a law has a symmetry G, namely the law is invariant, the structure of the law is invariant under the action of the operators in G. That's an intrinsic feature of the law, but something that's fundamentally relational. So it's like if a relational property of something that is itself relational, right? This is really structural. And these do a lot of work in structuralism. So what do we mean by structures? Well, so far we can say this: structures include extrinsic properties, relations, laws, and symmetries, right? We're getting towards what philosophers call an extensive definition, defining something by just saying what things have it. But this is not intended as exhaustive, right? For one thing, science is going to develop and other things are going to come into the fold. So as Holger Leary puts it in a very nice paper, Structural Invariance, Structural Kinds, Structural Laws, he says the present account, which is all about symmetry, is not bound to group structures. Surely symmetry groups play a dominant role in structuralism, but other structures come into play as well. The structural core of quantum theory is, for instance, given by the non-commutative algebra structure of the observables. It is, again, a physical, not a metaphysical question, what the fundamental structures in nature are. right? So structuralists don't want to nail this notion down too cleanly. They want it to develop. And if you are familiar at all with what Van Frassen's argument for why you should not consider physicalism a doctrine but a stance, you might now be able to see how this argument is going to go. Okay, but if not, just hold tight. All right, so that's the end of the first section, just defining what we mean by ontic structuralism as I understand it. Let's move now to consider, to assess ontic structuralism, right? And in particular, assess the claim, are elementary particles determined by structures? Now, the relevant structure here is taken to be group structure, okay? This is the relevant kind of structure that's usually invoked when talking about the definition of elementary particles. So James in his book, James Ladyman and Ross write, given that we've argued that relational structure is more ontologically fundamental than objects, we need to say something about how objects ought to be regarded. Now, when it comes to fundamental physics, objects are very often identified via group theoretic structure. So really what they're saying here is that symmetry structure, or what they're going to argue, symmetry structure, group theoretic structure is more fundamental even than elementary particles. So this is something structuralists think. You find this rhetoric all the time amongst physicists as well, in the Nobel Prize acceptance speeches, in the popular literature, in the propaganda, right? You often find claims like this from Steven Weinberg. At the deepest level, all we find are symmetries. Matter itself dissolves, and the universe itself is revealed as one large reducible representation of the symmetry group of nature. I'll say a bit about what that means in a moment. So ontic structuralists presumably are going to take some kind of backing from the fact that Nobel Prize winning physicists say the same thing. Ontic structure realists also, you could read us as giving a kind of critical analysis to this kind of rhetoric. And I would argue that actually makes ontic structuralism a really important intervention, not just in metaphysics, but in science. In the interest of time, I'm not going to explain why I think that is, but if anyone wants to ask me why I think this makes ontic structuralism scientifically important, I'd be happy to talk about it in questions. But for now, time is short, so let's move on. So my claim is going to be that this is false, right? It isn't the case that elementary particles are less fundamental than symmetries, despite the fact that lots of people in this literature think it is. Now, the fact that so many people think that this is, so many obviously extremely well-informed people think that this isn't the case, right? That symmetries are more fundamental than even elementary particles means that there's something at least very plausible about the idea. So I want to take a minute or two to explain why people thought this in the first place, okay? And to do that, we need to take a very brief detour called through group representation theory. Now, I'm going to just give the way stations on the road through this argument. You can find this all through the physics literature. I summarize some of what's going on here in this paper, but let me just give the kind of flavor of how the argument goes. So we've seen that ontic structuralism is supposed to be motivated directly by advanced physical theory as we now find it. The most advanced physical theory that we have is the standard model of particle physics. Now, the standard model has a very high degree of symmetry, famously. It has external symmetry or spatio-temporal symmetry in the form of Poincare invariance, which expresses its relativistic structure, and internal symmetry, which corresponds to symmetries of interactions in terms of gauge invariance given by this pasted together gauge group here. Now, this fact has some profound implications for the states of the systems that evolve in accordance with those laws. So this is first shown in a tour de force by Eugene Wigner in 1939. So what he showed in that work was that, we have a law, say in this case, the law of the standard model. Obviously, that law is going to have associated with it a state space. What Wigner showed is that when you have symmetries, that state space comes parceled out into what are called irreducible invariant subspaces, also known, little improperly, as irreducible representations or IRIPs. It's ugly but shorter. Now, the point of one of the salient points of this is that when a particle, say, evolving in accordance with the laws of the standard model, starts out in one of these subspaces, it stays there, right? It cannot come out of this subspace. The next important feature is that each of these subspaces or irreducible representations is the whole subspace comes labeled by the eigenvalues of what are called the Casimir operators, which is a set of operators that can be constructed and that are unique to each symmetry group, right? It's their job to commute with every element of the symmetry group. And so as such, they sort of represent constants of the motion. So what that means is the Casimir operators label the whole representation. So every state available to our particle has the same value of these, regardless of what state it is in. Okay, they're state independent properties. Every state available to them has the same value of these operators. So as such, these operators and their eigenvalues could be said to represent essential properties of the system. Regardless of what state an electron is in, it's always an electron. So you can see already that there is this really intimate connection between symmetries and kinds. So to take a couple of examples, very famously, this is what Wigner was analyzing. When you look at the Casimir operators pertaining to the Poincare group, there's two. One is the square of the 4 momentum vector, the eigenvalue of which, of course, gives the mass of the particle. And one is this object here, which is constructed from the Pauli-Lubansky vector, which has components angular momentum and linear momentum. And you stare at that long enough, you see that can be interpreted as a covariant spin operator. So what we can see is that this symmetry, the underlying Poincare symmetry of the standard model, explains why these two determinable properties of mass and spin always occur together. All the properties of the standard model have both mass and spin. That's really cool. Moreover, it turns out that the symmetry puts constraints on the determinate values, i.e. the magnitudes that these properties can have, either individually, both individually and together. So you can show through this analysis, more or less, that the mass has to be a non-negative real number, that whenever the mass is 0, the spin has to take on an integer value, and whenever it's greater than 0, it can take on integer or half integer values. That's the spin. Okay, so it's really powerful. But what's important to note, however, is that there is an irreducible representation, right? A pair of masses and spins corresponding to every pair of allowable values here, right? So there's an irreducible representation corresponding to, say, every real value of the mass, non-negative real value of the mass. Okay. So this is powerful stuff, and structuralists have maintained on the basis of things like Wigner's famous analysis that properties like mass, charge, and spin are structurally derived intrinsic properties, right? This is an idea that's quoted in Ladyman and Ross, where they write a group theoretic definition of an object, takes the group structure as primarily given, group representations are then constructed from the structure and have a mere derivative status. Likewise, Fred Muller says, the associated Lie algebra, think of that as the group structure, generates the Casimir invariants among which we find mass and spin magnitude. These are properties of the physical system under consideration. These properties thus are determined by symmetry relations, which makes them acceptable for the structural realist. Hence, ontic structuralism is a tailor-made version of scientific realism for quantum mechanics. So these are the statements you find. I would argue that this just isn't true. It doesn't follow. Now, the reason for this is that for structure to be prior to elementary particles, all properties of those elementary particles need to be derivable from structure, right? Remember, we think of the fundamental as a sufficient condition on the non-fundamental. Fix this, everything about the non-fundamental is determined. But this just isn't the case. So we've seen that properties that among the properties that define elementary kinds, right? We find that the magnitudes, determinate values of mass and spin. But which of these particular masses of all the continuously infinite number that are permitted by the group representation theory, one for every real value of the mass, say, non-negative real value, which are realized in nature usually has to be settled by experiment. Okay, and this is why there are so many free parameters in the standard model, which is something that a lot of people know about the standard model. So for example, when you think about particle masses, yes, there's a lot you can deduce. You can deduce that the photon and the gluon, it turns out, the gluons are massless and have spin 1, but we cannot deduce from the symmetries of the standard model the mass of the 6 quarks, the masses of the 3 charged leptons, the mass of the Higgs, or the mass of the 3 weak bosons. So here's Feynman. We have some 24 or more, I don't know the exact number, mysterious numbers associated with masses. Why is it that the mass of the muon compared to that with the electron is exactly 206 or whatever it is? Why are the masses of the various particles, such as quarks, what they are? All these numbers, right, which amount to some 24, have no explanations in these theories, absolutely none. There's no idea at the present time in the theoretical structures that I've heard of, which will give us a clue where these masses come from, okay? So the masses of most of the particles in the Standard Model are not determined by the symmetries of the Standard Model. Similarly, for the charge of the electron, we also don't know why these so-called 3 generations of matter, right? It goes on. Now, to be fair, there's other mathematical resources in physics that you can draw on here to try and help, kind of narrow things down. So for example, of a fundamental theory, like, you can, in quantum field theory, you can ask of a fundamental theory that it's asymptotically free, so well-defined in the high energy limit and sort of mathematically tractable. That's going to turn out to put an upper limit on how many of these free parameters there are. But it doesn't get you very far. It doesn't determine what the masses of the particles we find in nature are. So bottom line, there's this powerful connection between symmetries and kinds for sure, but symmetries don't determine the fundamental kinds as far as we know. And so they're not more fundamental than those kinds. Now, I would say here that it's perhaps confusion on the distinction between determination as a way of thinking about the fundamental and ontological, thinking about it in terms of ontological dependence that's maybe obscured this point, which is in retrospect pretty obvious. So you could say that for there to be electrons, right, there have to be symmetries, right? For there to be any physical system at all, there have to be symmetries, right? If you don't have some kind of temporal invariance, you don't have repeatable experiments, you don't have physics. If you don't have some kind of spatial invariance, you don't have intersubjectivity, okay? So absolutely, particle kinds depend on symmetries, but that's not the same thing as saying that they're determined by them. And that's how we should think about ontological priority. Okay, so what can the structuralists do if they still want to maintain this on the basis of current physics? Well, the general sort of line of escape is to claim that these determinate values of mass, say, despite by assumption being intrinsic properties, are themselves somehow structural features, and as such can be regarded as brute, right? If you can maintain that mass, considered as an eigenvalue of a Casimir invariant, which is a sort of mathematical structure, right? It's a mathematical operator intimately connected to group structure. If you can say that despite being an intrinsic property, that's a structural feature, you don't need to be able to determine it, right? Because any more than you need to determine why, the fundamental laws have an SU3 gauge group. That's just a brute fact for the structuralist, right? It's part of what's fundamental. So is there a way that the structuralist could argue this? Possibly, yes, right? So this one way that you might argue this is to point out that mass occurs as an undetermined parameter in the Standard Model, but what it attaches to directly are fields, right? The Standard Model is fundamentally a theory of fields interacting with one another, those parameters attached to fields. But maybe you could argue that fields are structural entities, right? So these undetermined parameters are just features of structure, features of structures. So this is something that Fred Muller has claimed. So to be clear, he's not using this to answer the argument just given, but he's one of the people that claims that fields are structural entities. And thus this represents a kind of way for the structuralists to get out of this problem that's kind of non-ad hoc, that has a basis in the existing literature. So as he puts it, enter structuralism. There are no particles at the fundamental level. There are only structures and object-like features of structures. What seems the fundamental substance of physical reality are quantum fields. Quantum fields are structures. With object-like features, the field quanta, right? So maybe that's one way to go. Another way to go is to claim that it's the group, together with one or other of its associated irreducible representations, that comprises what you mean by group structure, or at least the relevant structure. Now, this is something that Stephen French, who I really hope would be here today, has argued, and pretty somewhat explicitly, in the face of an argument of the sort I've just given. So this occurs in a very interesting, very rich discussion of how to incorporate modality into structuralism, maybe chapter 8 or 10 of his book. In any case, he writes this. If both the group and certain specific representations are included in our fundamental base, we can either take the representations as strictly non-structural, or take the whole package of symmetries and representations, that means, as what we mean by the structure of the world. My own inclination is towards this latter option. After all, what we are really interested in here is not the structure, but the structure of the world. And to cash out that definite article, we have no option but to bring in specific determinate elements, okay, akin to initial conditions. So these are two ways that the structuralists might try to get out of the argument that I've just given. And if we do that, then we're expanding the definition of structure to include not just extrinsic properties, relations, laws, and symmetries, but also fields and also irreducible representations. Now, here's the question. Can we do that? Do each of these things count as structures? Now, I don't know what the answer to that question is. I'm not sure that we have enough criteria to answer that question, but I do know what this dialectic reminds me of. And it is Van Frassen's argument that physicalism should be not taken as a doctrine, but as a stance. So in the last 10 minutes, I want to just very briefly introduce Van Frassen's argument for how to understand physicalism. And then I'll argue that this argument that I've just given shows that we should understand, or suggests we should understand, structuralism as a stance, not a doctrine as well. Okay. So Van Frassen's name keeps coming up today, and no wonder. I use it. Everything that comes out of his mouth is incredibly interesting. And his argument in the empirical stance that materialism and physicalism should not be regarded as a doctrine, but as a stance is no exception. So what Van Frassen here argues is that physicalism should not be regarded as a certain doctrine or thesis, namely the thesis that fundamentally everything is physical, right? But this is taken to be the descendant of materialism, which is the claim that doctrine that fundamentally everything is material. Rather, he says, you should understand these as a cluster of attitudes and a set of heuristics for research. So how does he get there? Well, he begins with two uncontroversial claims, namely that for physicalism or materialism to qualify as a thesis or doctrine, it must make a claim about how the world is. And to count as a substantive thesis, it has to rule something out, right? Totally unobjectionable. Then he argues, does the thesis that matter is all there is rule out at least some kinds of theories? I will argue that this is quite illusory. He continues, the thesis matter is all there is certainly sounds like a substantive factual claim. Does it not rule out Descartes' mind-body dualism, Aquinas' souls, spirits, vital principles, cosmic purpose? If those are substantive factual claims, then a thesis that contradicts them must be too. So suppose the thesis is indeed the important part of materialism. Then something follows from this about what materialists will find it important to do. It means they will certainly not rest until the distinction between matter, what is matter and what is not matter, has been made so clear that the thesis is a factual claim, which can clearly be seen as either true or false. But if they do not, then by modest tolerance, we should conclude what? So Van Frassen goes on to claim, among other things, that what materialists and physicalists do is, rather than giving a clear definition of what is physical or material, right, that clearly excludes certain things, they settle for pro-tanto definitions that they do not take to be binding. What that means, or what that allows, is that putative counterexamples don't refute the thesis, but rather simply show that the definition needs to be liberalized. Okay, so a little potted history here he gives. What counts as material, right? Let's start off with Descartes. Matter, by matter, I mean extended substance. So then you might say, well, what about Hertz's point particles? Do those falsify physical materialism? Presumably not. So let's say what we mean by matter is substance, extended or not. Okay, well, what about Newtonian forces between substances? Those aren't bits of matter. Do they refute physicalism? No, of course not, right? This is the perfection of materialism. So let's change what we mean by material to substances, extended or not, plus forces between them, right? These are all at least materialistically acceptable in some sense. So what about electromagnetic fields in addition to charged matter? Well, let's incorporate them too. So it's going to be matter is matter, extended or not, plus forces between them, plus fields. Then you might ask, what counts as an acceptable kind of field, right? All the fields posited in physics as it transitions are radically different. How do we know they're all physicalistically acceptable? And somewhere through this transition, matter fades into the background and we start talking about physicalism. So as Van Frassen says, how did the materialists know in the 19th century that the electromagnetic field was material? And how did later materialists persist in this conviction after the ether had been sent packing? How do you know that the classical electromagnetic field is material? What criterion are you drawing on? So it's pretty clear what the implication is from this, and this is that any future developments in physics are going to be accommodated. Whatever they posit will come under the rubric of material or physical. But then, says Van Frassen, if mental phenomena or cosmic purpose have to be posited, then those are just going to be count as physical too. Moreover, there's no reason to say that they won't, right? So you could think of the Copenhagen interpretation as being something that's kind of looking like it's starting to posit sort of irreducible mental substance to get around really fundamental problems in physics. So it seems physicalism rules out nothing. There's nothing that it can't sort of, incorporate within it. So putting everything together, Van Frassen says physicalism is not a doctrine, but rather a stance, a set of values, desires, attitudes, commitments, heuristics. And I'll just quote him here. It is quite clear now, the new conclusion that the newly introduced entities like fields are material too is not a matter of knowledge at all. But what is it then? If the physicalist or naturalist part of this philosophical position is mainly the desire or commitment to have metaphysics guided by physics, then that is something that cannot be captured in any thesis or factual belief. Hence, I propose the following diagnosis of materialism. It is not identifiable with a theory about what there is, but only with an attitude or a cluster of attitudes. These attitudes include strong deference to the current content of science in matters of opinion about what there is. As he says, though, this does not reflect badly on materialism necessarily. On the contrary, it gives materialism its due. So, this is a rather famous discussion of Van Frassen's. But what really strikes me now is the similarities between physicalism and structuralism on this score. So as doctrines, both of them are kind of forms of materialism. Everything is blah metaphysics. Everything is physical, everything is structural, right? On the one hand, on the other hand. As we've seen, both of them are resistant to defining their central posit in committal ways, partly because we expect the physics to evolve. As Van Frassen says, right, if physicalism is a stance, it's a commitment to defer to physics with respect to what there is. Structuralism does that too, right? It's supposed to be supported by our most advanced physical theory. So this invites the question, if structuralism is a stance, then it's a commitment to what, right? It can't just be a commitment to defer to physics with respect to what there is, right? Lots of philosophies, lots of metaphysics do that, but there aren't structuralism. So for me, to my ear, if structuralism is a stance, it's the injunction to foreground in metaphysics that the language of physics is mathematics. Never forget that everything in physics is understood through and through in mathematical terms when you do metaphysics. Now, this will seem like really obvious to, if you're a physicist, say, like, why would you have thought otherwise? But it's a point that's really lost on a lot of metaphysicians, I hate to say. So just to say, just in the last minute, to give an example of this, so I'll use David Lewis, which means Stephen and others, James have used as a whipping boy, which is a bit unfair because he's such an amazing philosopher in so many ways. But in any case, he's an egregious neglector of the fact that everything in physics is described mathematically. So famously, David Lewis argues that nomological structure is not fundamental because what the laws are is just settled by a bunch of facts about how little objects happen to be behaving in space and time. Move them around a bit, you get a different set of laws of nature. It's all fine. Don't need any primitive necessity to understand this. So he, in his Plurality of Worlds, Tour de Force, he writes the following: I support the denial that laws are necessary by means of the principle of recombination. Start with a world where the quark colors and flavors figure in the laws that are supposed to be essential to them. By patching together duplicates of things from this world, playing sort of chop and change, we can presumably describe a world where these laws are broken. Right, so what he seems to be saying here is take the quarks out of this world, put them in another world with their colors, just move them around with respect to one another, and you'll get a whole different set of laws. Well, if you remember that quark color is understood in terms of an irreducible representation of the SU3 group, indeed an SU3 gauge group, it turns out that when you transport that quark with its colors to another world, you're just going to get exactly the same laws back, right? For that particle to be a solution to laws, those laws have to have an SU3 structure. If it's an SU3 gauge structure, take my word for it, the law is just nailed down once and for all. There's no modal freedom there at all. So I elaborate on this in one of my papers, but I hope that this is enough to kind of suggest to you that the structuralist stance, if it is this injunction to mathematicalize your metaphysics, it's a very, very powerful heuristic. Nevertheless, if I had to put money on it, James in particular is not going to like this. Because in a very nice paper with Robin Brown called Structuralism, Physicalism and the Fundamental Level, no, Supervenience, Physicalism and the Fundamental Level, James argues that Van Frassen is totally wrong about how he thinks about physicalism, because while physicalism doesn't prescribe in advance what's physical, it definitely rules something out, namely irreducible mentality. Okay, so we see rights there, or they right there. Van Frassen fails to identify the essential negative content of the materialist tradition, its denial of mental or spiritual substance. So, right, see, versions of the Copenhagen interpretation would just scupper physicalism, right? Van Frassen is not right that it doesn't rule anything out. So, what should we say about structuralism, right? To make progress on what the doctrine of structuralism is, and to really convince yourselves it's more than a mere stance, not that that would be a bad thing, but to establish that it really is more than a stance, we really need to be clear what exactly it is that it rules out. Does it rule out fields as qualifying as structures? Should we count fields as structures or not? Does it rule out irreducible representations counting as structures or not? I actually find it really, really hard to answer that question. So I'm not going to try and do that. I'm going to pitch it to Stephen and I think also Fred, who's here. So we can have this conversation among ourselves, but I hope the importance of the question at least is clear enough. I'll just finish by saying thanks. I'm going to plug the Society of the Metaphysics of Science conference. We're accepting papers, please apply. And there are some references on eliminative structural realism. Thank you very much.
Thanks so much. That was a fantastic talk. Thanks, Kerry.
Thank you. Great.
I already see a bunch of hands. Before we get to hands, I did have one very minor technical question. And I think this is an incredibly minor point, but on an earlier slide, Kerry, I think you indicated that in the m=0 case, you can only have integer spin.
Well, it's like helicity.
Right. But, like, as an example, neutrinos are spin half particles. And, although some neutrinos are believed to have mass, it's not known for a fact that all of them are massive. So super minor technical point. I just thought I would mention.
Yeah, thank you. Thank you very much.
No problem at all. So I see, it's great. So I see a whole bunch of hands. I think, let's see, whose hand was first? F.A. Muller, go ahead.
Hi, Fred.
Okay, thank you, Kerry, a wonderful talk. I'm still a bit in mystery about your exact argument against the group theoretical derivation. What one is deriving by means of these group representations is the existence of essential features of the structure. That's how I would put it. And a dimensional analysis will reveal that one of these essential features has the unit of angular momentum, another one has the unit of mass, and so they are easily identified with what is called spin and mass in physics. What is not determined is, of course, the exact values, but that would be requiring of the philosopher of science that he determines the value of Planck's constant. And I think that is putting the bar so high that no one will ever be able to get across it, right? So that is not that is not part of the claim that the actual values can be deduced from space-time structure in this case, but that there are intrinsic features and what kind of features they are.
But I mean, well, never say never. I mean, one of the reasons people think the standard model is not fundamental is because it leaves too many things like masses undetermined, right? There's this feeling that as physics is going to progress, right, more and more of this will be shorn down. And the very fact that we can already do this with at least some of the particles, like the massless gauge bosons, shows that there's no kind of it's not clear that there's some in principle impossibility about this. But I mean, it's an incredibly high bar to clear, but if you want to make some radically revisionary metaphysical claim, you should expect to have to jump over a high bar. And it just, I mean, I think it just follows analytically by what it means to say that a particle kind is not fundamental. It's less fundamental than symmetry. It means that every feature of it is determined by that symmetry or by whatever it is that you take to be fundamental. Now, you can give arguments that say its spin is determined, right? You can give at least heuristic arguments why it has to have spin half. It has to belong in the fundamental representation just because it's a fundamental particle and you're going to use it to build up other ones. But I just think it follows analytically that that's how you have to think about it. And it's an open empirical question whether physics is ever going to be able to jump that high bar. I would never say never, but it's not supported in current physics.
Okay, thank you.
Thanks, Fred. So Mahmoud, you're next.
Thanks. Thanks for this talk, Kerry. It's great. My question's related to Professor Mueller's question, I guess, which is where do you think that structuralism about mathematics comes in? It seems like if you think that ontic structuralism is where you're committed to taking seriously the mathematical structure or nature of physics in your theorizing, then it seems that you're implying that ontic structuralism kind of comes with mathematical structuralism. And that seems fine, but then there's this sort of worry that was brought up that if you're criticizing ontic structuralism on the basis that it can't determine values, that's asking too much, because in mathematics, you don't think that there's something else you need to determine by experiment to specify the group structures. And you might think then that you could understand this worry about that a theory isn't fundamental because we can't determine the values of masses or things like that. Is this methodological sort of motivation that whenever we have something that's intrinsic, we take that as a problem to then sort of get the structure, a deeper structure to explain that. So my question is just where do you think mathematical structuralism comes in?
Oh, goodness me. I mean, it's not obvious to me. I've never worked in mathematical structuralism. It's not obvious to me that it really helps at all. Like, I absolutely get, I get that if you're going to make a claim, like symmetry is fundamental, right? To order to not sound like a Platonist, you have to give some kind of, not just an operationalization of that claim, which in a way we could already give, but rather some kind of physical implementation of that claim. And it's not obvious how to do that. So people that are a lot more subtle and careful than me have tried to do that. So David Schroen has a paper just out in Phil Quarterly where he really talks about what it would mean for, in a physical sense, for a law to have a symmetry, and other people have done something similar. But I suppose in some sense it's just another instance of the applicability of mathematics, which is a huge question for structuralism. But in some ways I want to say my conclusion just holds independently of that. We know what the symmetries of the standard model are, however it is that we sort of interpret them or translate these claims about symmetry into the world. But we also know that there's nothing in that allows us to determine what the spectrum of particles is in its totality. And that just suffices to show to me that it's not fundamental. But I mean, I'm also sort of with James here in that, when we spoke about, something like this having a face having a symmetric structure, it's never obvious that that's an intrinsic property or any kind of geometric feature. Being rectangular, right? These shape properties are often presented by metaphysicians as intrinsic properties. That's fair enough if you're dealing with an abstract geometric figure, but there's never anything obvious about intrinsicality. I think that's what James was getting at when it comes to physical things, where when you learn physics, you just learn everything depends on everything else. So there's a place for thinking about how these questions play out in, abstract mathematical regimes where you're not worrying about physical implementation. And there's just also a way in which they those kind of questions can completely misrepresent the real metaphysical questions as well. So it's just a huge issue. I know that's a really disappointing question, but that's what I'll say.
Thanks. We had
Thank
no
you.
more hands. James did have one comment in the chat. James, we have to move on to the next talk. Is it okay if we address your question after during the hour question period?
Are you talking to me? No, I didn't. I just put that in the chat for people to think about. I don't need it to be addressed at all. Sorry.
Okay, no problem at all. All right, so let me stop the recording.